in this case 2 to the x, that's how the calculator understands it. You can go to the table of values to get the points, but you can also have a quick look at the picture, zoom 6. So that's what it ought to look like, but we get the points from the table of values. So I'm going to start off at -2. -2 gives me 1/4, 0.25. -1 gives me a 0.5. 0 gives a 1. 1 gives a 2. 2 gives a 4. And 3 gives an 8. All right. So what we're looking at here is a relationship where each value is getting multiplied by 2 to give the next value in the list. All right. So 0.25 times 2 would give you 0.5, which in turn, multiplied by 2, would give you a 1, and then going from there, you get the rest of the list. All right, that's the nature of an exponential function. All right, so it's always multiplied by the same value. All right, call that a common ratio, but we'll get to that on the next page. So I want to plot these points, -2 and 0.25, roughly. Yeah, doesn't have to be perfect. -1 and 0.5, 0 and 1, 1 and 2, 2 and 4. The next one is 3 and 8. We could go further, actually. There is enough room. So if we do that, all we would need to do to come up with the next point would be to double the value of the most recent one. So 3 gave an 8. Double 8 is 16. So at 4, we would have 16. All right. We could also figure out some other values along the way, but they're already so close to the x-axis that it may not even be worth it. But if you were wondering, to go to the left, we just chop these distances in half. So we started off, really this is our benchmark. We started off with this value of 1. All right, that's going to be the case for every exponential function. To go to the right, we multiply that by 2. All right, so the height, this particular one here, can be determined by 1 times 2. All right. Going the other way, this height can be determined by taking 1 and dividing it by 2. All right. So if we're constantly dividing by 2, then we can go further and further away from the origin. All right. But half of a quarter is an eighth, a 16th. Before too long, it starts feeling like it's going to get merged with the x-axis, even though it never does. All right. This is what we have here is an asymptote. That's a curve that approaches a line but never actually gets there. But to actually draw an asymptote is kind of tricky because it almost always looks like it's going to merge at some point. So you just do the best you can with that. But this is what the curve should look like. And if you could go on further, but we're out of room, so this is where we would end it. All right, so this is f of n is equal to 2 to the nth power. All right. Now the next table that we have to fill in based on the next function, really it's got the same base component as this one. So you could actually look at this as the parent of this function here. All right. So if you take all of the transformations and strip them away, you would just be left with 2 to the nth power. All right. So you could create the graph based off of what you know about transformations. All right, but you don't know the general model yet, so we're better off just doing it by points. So if I go to the table of values in the calculator, I would change this to 3 parentheses 2 to the x power minus 1. Go to the table. I want to start it off at -2, so -2 and -0.25. Then positive 0.5. Then 2. 5, 11, and 23. The 23 is not going to fall on the grid. going to run out of room, so we won't worry about that one. But the other points we can get on there. Make it red. So at -2, I'm plotting -0.25, which would be about right here. 0.5 is what I would get at 1, so it's actually the same coordinate, or a same coordinate as the previous graph. 0, 2, 1, 5, and really just 2, 11 after that. It's enough to get a general sense of the shape of the graph, but we're kind of missing a key ingredient here, and that would be, what horizontal line is this graph approaching? Because if we make the assumption that it's going to have the same characteristics as the other graph, then it should level off and start approaching some horizontal line. Right? It's kind of hard to tell from here, but if I go into the table and grab a few more points, you get a better idea. So even though they didn't ask us, I can plot -3, comma, -0.6-ish. All right, so that's this one right here. -4, -8, 0.8, sorry. -5 is corresponding with about -0.9. Same idea for -6, just closer to -1. So it appears that this one is approaching a -1 y value, right, as it goes to the left. The other one was approaching 0, the x-axis specifically. This one appears to be approaching y equals -1. And so you look at the structure of the formula, or the equation, you see that this one has a -1 off at the end. All right, that's a vertical shift. All right, it's pretty much confirmed here, because this point, or well, not even a point, it's really a horizontal line. I just want to get a decent color here and go orange. This horizontal line was the line that the black graph was approaching. If I take that horizontal line and shift it down 1 unit, now I get the horizontal line that the red graph is approaching as you go to the left. All right, so you can get little bits and pieces from just the structure of the equation, but we do have to learn about what that structure is all about. All right, so what are the similarities and differences between the two graphs? Same shape and orientation. Different intercepts and asymptotes. So asymptote, again, is a line that the curve is approaching, and it's not going to get there, but it's approaching it. It's getting closer and closer, but it'll never actually intersect. Right. Linear functions, exponential functions. We have familiarity with linear functions. Slope-intercept form, y equals mx plus b, where m is the slope and b is the y-intercept. Y equals a times x minus h plus k. A little bit more involved, that's the point slope form, or one variation of it. A is the slope. H comma k is any point on the line, but it could also be thought of in terms of translations. So if you were to take the parent function of a linear equation, which is y equals x, and shift the points left or right, up or down, then you would get the transformed equation. All right. Exponential functions have in the same construct in terms of the a, h, and k's, but it looks vastly different. All right. So the a is the stretch or shrink. Right, same. A, H, and K are going to play the same role as they always have. Right, A is the stretch or shrink. If A is negative, there's a reflection over the x-axis. H and K gives the translations, but the new one is the B value, which is the base of the exponential. All right, so but it's also known as a common ratio. The common ratio is the number that you're multiplying by consistently to get from one value to the next. All right, so just going back to the graphing calculator, if I had something like 5 raised to the x power, going to the table of values, start off at 0 for x, you see that each value in the list is 5 times the number that came before it. So the common ratio would be 5. All right, if I made this a 9, for example, the common ratio is 9 because to get from each entry in the list to the next one, you multiply by 9. All right, so whenever there's that relationship, we're looking at an exponential function. Whereas if I had something like x plus 9, each entry is increasing by 1 because the slope is 1. Right? That's the common difference, the difference between the two values. All right? Now, if I wanted to have the difference between those two values be something other than 1, then I would make the coefficient of x something other than 1. So maybe like 9x plus 9. All right? So at 0, I'd have a starting value, a y-intercept of 9, but the difference between consecutive values is always equal to 9. That's how slopes work. All right? So if you think about an exponential base as, okay, same idea as slope, except you're multiplying instead of adding, it's not a terrible way to think about it. All right? So increasing, decreasing functions, it's really just more about the shape. I'm sorry, not the shape. The shape's the same. The orientation. All right? One starts low, ends high. The other starts high, ends low. As x increases, y increases. As x increases, y decreases. That could be true for lines. You know, you can have that relationship. It's just now we have to bridge over to the idea of, well, we can't just say, when I say what's the relationship between two variables, you can't just say as one increases, the other decreases. As one increases, the other decreases exponentially. As one increases, the other increases in a linear fashion. All right? So, like, we have to be specific about, okay, what's going on with the graph, but also what kind of graph is it? All right. So the example that follows, well, number 2. Hopefully I labeled this one number 1. Okay, good. One's exponential and one's linear. We got to tell which is which. We're looking for a common difference for linear functions and a common ratio for exponential functions. So in this case here, for the first one, if we divide any of the two values, so 10 and 5, for example, 10 divided by 5 is equal to 2. All right. I would just want to make sure that that ratio holds true every step of the way. All right. So 20 divided by 10 better also be equal to 2 if this is going to be exponential. 40 divided by 20 also 2. And then finally 80 divided by 40 also equal to 2. All right. That's a more elaborate way of saying we're just taking the first number, multiplying it by 2, taking that answer, multiplying it by 2, taking that answer, multiplying it by 2, right, and so on. So if you have that relationship, then we know it's exponential. So table 1 is exponential. And that's because it has a common ratio of 2. All right. Whereas table 2, it still has a relationship, it's just not a common ratio, it's a common difference. If I take the first two values and subtract them, 11 minus 8 gives me a 3. 14 minus 11 also gives me a 3. If I keep going down the line, the difference between consecutive values is always going to be equal to 3. That gives us a common difference, which steers us towards a linear function. All right, so table 2 is linear because there's a common difference, specifically of 3. But it's more important, not so much what the common difference is, it's more important that there is a common difference. All right, that the difference between consecutive values never change. That's how we know it's linear. The quotient or the product, depending on what perspective you take, the ratio between consecutive values, if that never changes, then there's a common ratio, making it exponential. All right. So then to write the equation of a line in standard form, we'd start off with our, well, the first one's exponential. So we start off with our exponential model, a times b to the x minus h plus k. And for the second table, it's going to be y equals a times x minus h plus k. All right. So if we can get a sense of any kind of stretching or shrinking, anything along those lines, translations, then we can piece together what the function is going to be. That being said, the common ratio is the b value. The common difference is the slope, which in the appropriate equation would be the a value. So we have what we need there. So y would be equal to, I don't know the a value, but I do know that it has to be 2 to the x minus h plus k. I just don't know anything else yet. All right, and for the other one, y is going to be equal to 3 x minus something plus something else. All right, so when it comes to linear equations, very easy. Just pick any one of the coordinates and plug it in and you're good. It doesn't matter which one you pick. All right, I go for the simplest one. 0, 8, anything that involves a 0 is going to be simpler. So minus 0 plus 8, which would actually simplify kind of nicely to y equals 3x plus 8. Then I would just do a quick check to make sure I didn't just totally botch that. Just grab another x value and plug it into the new equation and see what it gives you. For example, if I plug a 4 in here, 3 times 4 is 12, plus 8 gives me a 20, which is what it should give me, so I know I did it right. All right. You could also take this and put it in your graphing calculator and look at the table of values and see what comes up. This, in part, will come up in that table of values. Now, for the exponential one, the a value is going to be pretty easy, but the h and k could be a little tricky. All right. If there is a common ratio between y values, then there is no translation. There's no horizontal or vertical translation. All right, just going back to the example that we did before, it was 3 times 2 raised to the x power minus 1. All right, and the parent function of that was just 2 to the x. All right, look at them one at a time. If I look at 2 to the x, you see there's a common ratio between the y values. Multiply by 2, multiply by 2, multiply by 2, and so on. All right, this function, which is also exponential, does not appear to have a common ratio, which means, so looking at this, like what do I multiply 2 by to get 5? Yeah, 5 halves. But if I take the 5 and multiply that by 5 halves, I get 12 and a half. So that's not going to work. But we know it's exponential because it has the same structure, which means there must have been a translation. Right? There must have been some kind of movement in terms of the x or the y values, horizontally or vertically. All right? But because this graph here, if I can get this out of the way, this one here has a common ratio, it means that there was no horizontal or vertical translation. So I don't have to worry about subtracting off anything from the x or adding anything to the function. So then I got to think about, all right, well, if I'm assuming it's 2 to the x power, what does the coefficient have to be in order to get this array of values here? Well, one nifty trick has to do with the nature of an exponential. So if you look at any, and this boils down to like just the generalization that if you know it, you're in good shape. If not, you're going to want to know it. Any exponential parent function is always going to cross the y-axis at 0, 1. All right, so it'll always have a y-intercept of 1, basically. And I could show you really quickly. So let's say I have, well, I already have 2 to the x in there, so let's say I have like 1.5 to the x power. Let's say I get throw a fraction in there, another type of fraction like 0.25 to the x power. Oh, hit the wrong thing. X. And then let's say I throw in like a 4 to the x power. You know, just a few different varieties here. Turn this one back on. Do a quick zoom 6 to get a look at the picture. You got a bunch of different exponential graphs, all plotted simultaneously. It looks wonderful. But if I take a closer look, zoom in, zoom option 2, bring my cursor to where all the magic's happening there and hit enter, it appears that they're all crossing the y-axis at the same exact point. All right, so any function in the form of y equals b to the x power will have a y-intercept equal to 1. Okay, so then I would ask myself, all right, well, what is the y-intercept in the new graph? Well, I have a y-intercept of 5. And I already ruled out a translation. So it must have been a stretch that got the 1 to a 5. So the a value must be 5. All right. A simpler way of thinking about it would be if you take the parent function and figure out what you'd have to multiply all the y values of the parent function by in order to get the values in the table, then you're good to go. So just going back to the graph again. Let's say I only want to look at 2 to the x power. Line it up with what they have. Like in this case, the parent function is giving y values of 1, 2, 4, 8, and 16, the relevant ones anyway. All right. So I'd ask myself, well, what would it take to make the 1 and 2 a 5? Multiply by 5. Will that work for the 2? Yes. 2 times 5 is 10. 4 times 5 is 20. 8 times 5 is 40. 16 times 5, if you didn't know, is 80. So it checks out. So we have our function here, and there's really nothing else to do with that, right, which is kind of nice. So it's a matter, in most cases, of identifying whether there's a common ratio, and then if there is, you just got to figure out what the stretch is. All right. Now, number 3, to get from a 32 to a 16, it could be the case where you divide by 2 or multiply by 1/2, but that won't get you from the 16 to the 0. All right. So this must be a subtraction kind of deal. So we tend to think only in terms of addition and multiplication. So we don't say that we're subtracting. We just say we're adding a negative number. Instead of saying dividing, we just multiply by fractions. All right. So in this case here, it looks like I'm subtracting 16 across the board. In each case, I have a common difference of negative 16. That's the same as if I were to say, all right, well, what's 16 minus 32? Negative 16. 0 minus 16, also negative 16. Negative 16 minus 0, also negative 16. And then 32, negative 32 minus a negative 16, also negative 16. All right. If you needed to demonstrate the common difference, this is how you would do it. But you don't often need to do that. All right. But once you identify a common difference, or identify that there is a common difference, then we say it's a linear equation. with a common difference equal to negative 16. The form of a linear equation. Now they said y equals mx plus b. That's ultimately what we wanted to simplify down to. We're using y is equal to a times x minus h plus k. The common difference is the a value. You just have to pick a point from the table in order to get the h and k values. All right, so go simple. 0, 0. Put in a 0 for h and a 0 for k. This is going to end up being pretty clean. Y is equal to negative 16. X minus 0 plus 0 is just an x, so not worried about anything there. So y is equal to negative 16. For the other one, we want y is equal to a times b to the x power. They said by using this notation, they basically told us that there's no translation involved. So that's great. All right, we would have figured it out anyway because we have a common ratio here. 6 divided by 2 is equal to 3. 18 divided by 6 is equal to 3. 54 divided by 18 is equal to 3. And 162 divided by 54 is equal to 3. So this is exponential with a common ratio equal to 3. All right. So the common ratio is going to be your base. That's your b value. The a value is whatever the multiplier is that gets you from the parent function to this array of data. But I think the cleanest and simplest way of doing that, or figuring that out, would just be determine what the y-intercept was multiplied by in order to get the y-intercept of 0, 1 was multiplied by it in order to get the new y-intercept of 0, 2. All right, so that must mean that the stretch factor is equal to 2. So y would be equal to 2 times 3 to the x power. All right. So if I put in a 0 for x, 2 times 3 to the 0th is well, 3 to the 0th is 1 times 2 is 2. If I put in a 1 for x, 3 to the first power is 3 times 2 is 6. So it's all checking out. All right. So for the parent function, the y-intercept should be 0, 1. For this new array of data, the y-intercept is 0, 2. All you're doing is figuring out what 0, 1 had to be multiplied by in order to get 0, 2. When you think about it that way, it's very simple. All right, so your assignment is just the back side of this. Well, oh, actually, no, sorry, not the back side. I forgot. I gave you a new separate sheet. Going